12.7 is where we take logarithms and the ways we've learned to solve logarithmic equations and exponential equations, and we apply them to actually do some word problems. And this is a very important section because a lot of people who stop at Algebra 1 and don't move on to Algebra 2, they never really get a good understanding that a lot of things in the real world have an exponential type of pattern to their growth. And if you don't understand how to work with logarithms, you might get that in a vague sense, but you'll never be able to work it out very specifically. And lots of the real world depends very heavily on how exponential growth and decay work. The basic idea behind exponential growth is that you might have some sort of a starting amount, and then over time the amount that you have will grow, but it doesn't grow in a straight line. Exponential growth is where it curves up and it grows faster and faster and faster over time. Lots of things have graphs like this. The population of the planet is curving upward. Technological growth curves upward. There's a lot of things in the real world that if you try to use a straight line to predict what's going to happen in the future, you're going to miss the mark by a really long shot. So it could be, in some textbooks, broken up into a bunch of different formulas depending on specific situations you're looking at. Are you looking at a banking problem? Are you looking at a population problem? Maybe you're talking about radioactive decay. Maybe you're talking about earthquake magnitude. And I think it's a really bad idea to do what those textbooks do, where they break it down into 6 or 7 different formulas. It's much easier, at least I think it's much easier, if we just stick to using one formula every time for every problem. It will add sort of an extra first step that we have to do where we tailor the formula to fit each individual problem we work on, but you'll only have to memorize one thing. So the formula we're going to use is this one. And it's really easy to memorize if you just turn it into a word. I mean, A equals PERT. And just remember that RT is an exponent and you're good. You've kind of already memorized the formula. So in terms of the hard part of memorizing formulas, done, taken care of. But then you've also got to know what the different parts of the formula represent. The big capital P in PERT, that stands for the starting amount. And when I say amount, you could be talking about an amount of money. You could be talking about a population, for P for population. You could be talking about some sort of abstract measurement of technology, like how fast are our computers or how much memory can my phone store. But you have some amount in a very, very general sense that you're starting with, and that's what P stands for. A is going to be the final amount at the end of whatever length of time you're talking about. T, I think it should be pretty obvious what T is. Nobody ever really doubts what that is. That's time. And then R is a thing called the growth rate. And depending on what you're talking about, some things have very, very slow, gradual growth rates, and some things have very rapid growth rates. Like if you're trying to measure like bacterial growth rates, they can double in like a few hours, and so it can have a very fast growth rate. Whereas things like human population, the growth rate for humans is actually kind of slow. It's just that there's already so many of us that there's a lot more being born every year. Another thing that you might wonder about, and this is a very important thing to wonder about, is what if R is negative? R, remember, is the growth rate. And there should be a really common sense idea here about what that should produce. If R is negative, that means you have negative growth. That means instead of curving up, the thing's going to curve down. And since the curving up was following an exponential curve, when it curves down, it should have the other type of exponential curve behavior, which is an asymptote. And that's a situation called exponential decay. So we use the exact same formula for exponential growth and for exponential decay. The only difference is, when it's growth, your growth rate is positive. When it's decay, your decay rate is negative. So the rate controls whether it's growth or decay. We are going to make 3 different videos here of 3 different examples because there are multiple different challenges in using this formula to actually accomplish things. The first example we're going to look at in this video is kind of an introductory level problem. Oops, scrolled too far. Having to do with a population. In particular, a population of rabbits. They were released on some island in, say, just picking a year, 2017. In 2018, there are 79 rabbits. Guess what? In case you weren't aware, rabbits breed like, well, rabbits. They breed very rapidly. And we're going to try to figure out how long it's going to take until there are 1 million rabbits on the island. Seems like it would be a long time since there's so few right now. It's probably a pretty deserted island and you can't even see all those rabbits, but when there's 1 million, there's going to be a bunch. So, here are the steps. First of all, make sure you have the formula memorized. A equals P e to the RT. We're going to be using that formula for this problem. The first thing you have to do in order to use that formula in this problem is you have to figure out what the growth rate is. So that's your step number 1. Find R. So let's read through and figure out which numbers get plugged in where, and then we're going to show you how to figure out what R is from that. So the starting amount here was 2. It was a pair of rabbits. There were 2 rabbits to begin with. The length of time at first is only 1 year. I mean, we started in 2017, and in 2018 there are 79 rabbits, so the length of time at first is just 1. And the 79 rabbits is the final amount in that 1 year. So this is sort of a mathematical description of what happened in that first year. From 2017 to 2018, the amount went from 2 to 79, the length of time was 1, and we don't know what R is. This is an exponential equation like we learned how to solve in 12.6. It's got an exponential equation where there's exponentials on one side only. So the first step is to isolate the exponential. To isolate the exponential, we have to divide by the 2. So we have 79 divided by 2 equals e to the r. Yeah, it's r times 1, but life will be easier if I say r. Then move the base to the other side. If you move the base to the other side, it's going to be the base of an exponential, but writing it as logarithm base e, that's not proper form. The proper notation for that is ln, just like it is on your calculator. So we should be saying ln of 79 equals r. So grab your calculator, figure out what that is. Natural log of 79 over 2 comes out to be 3.676, etc. 3.67630, etc. And just like with square roots, logarithms usually come out irrational numbers. Don't be surprised if these decimals are ugly messes. As we move forward into the next part of the problem, we have a choice to make. We're going to be using r in this formula again. We're going to take a equals p e to the rt, and this number is going to get plugged in for r. And the choice is, do we want to use the decimal, or do we want to use natural log of 79 over 2? And I know which way I'm going to choose. I'm going to use natural log of 79 over 2 because that's easier to write. It's less complicated to write it out. So now, in step 2, what you do is you use r in the formula to answer the question. So the formula now, we have an actual thing to put in for r. We have a equals p e to the natural log of 79 over 2 t. So the question is, okay, what was the question? What were we supposed to answer? So at this point, go back and read the paragraph again. Let's see, pair of rabbits, 2017, 1870. Here we go. To the nearest year, when will there be 1 million rabbits? So 1 million is going to be the final amount at the end of some unknown length of time. So what that means is we're going to plug in 1 million for A. P, remember, P was 2, started with a pair of rabbits. And T is a variable because we don't know what the length of time is. It's an unknown length of time. And then we solve this equation. And as you practice these sorts of questions, I guarantee you, you're going to start to feel kind of weird. It's going to feel like you're solving the equation twice. And the reason why it feels like that is we just did almost the exact same steps that we're about to do back when we did step 1. We moved the coefficient to the other side by dividing. We moved the base to the other side by turning it into a logarithm. And then we had to grab a calculator. Well, very similar steps are going to happen here. We're going to move the base to the other side, or move the coefficient, excuse me, how amateur. Move the coefficient to the other side by dividing. 1 million divided by 2 is 500,000. And then we're going to move the base to the other side by turning it into a logarithm. So it'll be log base e, remember, natural log. For calculator purposes, I don't think I want to put the commas in. There are no commas that are doing any good on a calculator. But there is one extra step here. T is not by itself yet. We've got to take that coefficient and divide it to the other side. But then we can just grab a calculator and make the calculator work out this computation here and see what we get. So let's see. Natural log of 500,000 divided by natural log of 79 over 2, 79 over 2, gives us 3.569447809. And this is another thing that you'll run into with all word problems. Not just here when we're talking about exponential growth and decay, but all word problems. When you're done with the algebra, with the math side of things, you still have to sort of wake up from your math trance and figure out, what does that number actually mean? The question was asking, what year will it be? Remember, it says, to the nearest year, when will there be 1 million rabbits on the island? And that's not a year. So we have to remember, this was all starting in 2017. So if it's a length of time of a little more than 3.5 years, starting from 2017, rounding to the nearest year, that's going to be in the year 2021. Notice, that's not that far away. That's only about 4 years away to get 1 million rabbits. This is why invasive species are such a problem. Even though they don't seem at first like they're being such a problem, their population curves upwards so fast that by the time you start dealing with them, they're all over the place and it's too late to do anything about them at all. So if you thought that the math that we were learning here had no practical use, invasive species are a real thing, and knowing how quickly they will catch up at you is a real thing. Remember, there are 2 more videos about 2 more examples of using this formula to answer questions.